All right. So this is a talk about physical memory aliasing attacks on RISC-V. So already today we've heard about BATRAM. When I joined, I didn't know about it. But it's a recent attack on AMD CPUs that breaks trusted execution environments, and it did not affect Intel CPUs, but because they already had some mitigation in place. But this attack was based on some modification of this SPD chip on the DRAM DIMMs, where you could create physical memory aliases. And now you may say, okay, what does RISC-V has to do with that? Because it's for embedded systems and so on. Well, it turns out that RISC-V boards that are more powerful are quite emerging in the market, and they have pluggable DIMMs, and they also try to populate servers in the cloud. So when we're talking about RISC-V and RISC-V isolation, we have three main modes: the user mode, the machine mode, and the supervisor mode. We also have hypervisors, but it's not in the scope of the talk. So in user mode, we have the user applications, and we also have our operating system with the kernel that isolates these user applications. But we also have machine mode, where there is the more privileged mode, where we have, for example, OpenSBI, which is a lightweight firmware. And when we add enclaves, we may have Keystone, a framework that creates trusted execution environment. We have the enclave application running in user mode, and we also have a trusted interface that runs in S mode that communicates also with the security monitor, which is a plugin, an extension of OpenSBI. So this kind of isolation is done using PMP, or physical memory protection. This kind of protection basically works on physical addresses, and you can think about it like you have some registers that you can configure with physical addresses, a region where that particular process will be isolated. So you can have your operating system running in read, write, execute permissions, and so on. You can have your enclave that is not accessible from other processes. You can have your firmware not accessible from other processes running in the machine. And so far I mentioned an ISA isolation mechanism that operates on physical addresses, and I've also mentioned a primitive that also messes with physical addresses and creates physical aliasing. So this should be fine. There's no problem. So if I want to talk a little bit about BATRAM, and we basically have this SPD chip that says to the CPU, hey, this is the amount of DRAM you have, and the CPU then will have a view, have the physical address space. But what if that SPD chip lies to you? So what if instead of 32 gigabytes, for example, we mention and report 64? Well, this will basically create an alias, and basically we will have the legitimate physical address, and then we'll have an alias physical address that map to the same DRAM address space. So what are the exact implications of BATRAM on RISC-V? So to investigate this, we provide native hardware support for Keystone, and we also do some attacks utilizing the BATRAM primitive on enclaves. And we also provide some mitigations. So this is our board. This is the Bulck 5 Pioneer board. It also has pluggable DIMMs. As you can see, we've labeled these DIMMs using post-its to differentiate between the BUD-RAM ones and the non-BUD-RAM ones. It has 64 out-of-order cores, and yeah. And some more information about this board is that its boot process consists of an ARM system processor that then transfer the execution flow to a zero-stage bootloader that performs some initialization of the hardware that then goes to the actual system firmware, which is OpenSBI in this case, and then your operating system and so on. Some engineering effort was done. More details are in the paper, but what I want to focus here is that in this case, we needed to modify the integration of the security monitor with OpenSBI because Keystone works with a very old version of OpenSBI and newer hardware, well, it's newer version of OpenSBI. And we also modified the zero-stage bootloader to have secure boot and a pair of keys for attestation of the enclaves. And then we could move to actual attacks. So here is an example of just creating an enclave where that is shown in gray, and it's isolated using PMP. So the memory of the enclave is isolated from, for example, other processes and the security monitor and so on. And there we can have, for example, a secret that maps to memory. But we also have the aliased space that corresponds to that enclave. And basically, to calculate that alias space, all we need to do is calculate the offset mask, and we can basically use that offset mask to find the alias for a physical address. And this way, we can leak arbitrarily memory of the enclave. So I've also mentioned attestation. During the boot phase, we generate a private and public key for the security monitor, and then the security monitor is able to attest an enclave for us. We have the verifier that generates a nonce. The security monitor will generate the report and return that for attestation. But an attacker actually can sit in the host, in the malicious host, and leak the security monitor's private key and forge a report that will actually be also valid and pass attestation. So what now? Mentioned some attacks, some feasibility. We actually try to provide some mitigation. Here we have the naive approach, where you just write the marker on each physical page, and then you try to read the marker. If the marker is actually corrupt, then you have aliases. But this is quite slow. Then, due to some work that was done by the ETH group, where they wanted to perform rowhammer attacks, they reverse engineered the memory controller for this board, which was very helpful, thank you, which enabled us to create a more optimized boot time detection mitigation. So to wrap it up, what is the main takeaway that I want to make from this talk is that many attacks that we've seen on other architectures, such as x86 attacks, are feasible on RISC-V. With BUD-RAM, we break physical memory protection, and we also provide some boot time alias detection mitigations with minimal overhead. We also have our experiments and modifications and whatnot in these frameworks, open source. You can find it in our repository. And yeah, thank you for your attention.
All right, so we have some questions.
Hey, very cool talk, thanks. So as I understand it, you did this on hardware, right?
Yes.
On this Memory-V, what is it again?
Memory-5 Pioneer.
Pioneer, right. And that one has the C910, C920.
C920.
Okay. So I tested PMP at some point on the C910 and it wasn't working. So that means on the C920 it now works?
Yeah.
Okay.
I don't have access to yeah, okay.
Because I would be interested, so like the C920 is also affected by Ghost Write, if you know that.
Sorry?
So the Ghost Write CPU bug
Yeah.
should also be present on the C920, so I would be interested if that breaks PMP too.
I didn't try it, but
I guess let's try later.
yeah.
Thanks.
Thanks for the talk. So if I understand correctly, to do the attack, you have to have physical access to the device to go to the bad RAM. You can't do that remotely, right?
So one way to do it is with physical access. One other way to do this is you can do this from software fully if the SPD chip is exposed, and yeah. So you can do this. You can have a fully physical attack, but also a fully software attack. We've actually did this, also this test that we could do this in the board and actually it's exposed on this board. So you can do a fully physical attack, fully software attack. Yeah.
Thanks for the great talk. Can you actually comment on the security of the boot chain on these devices? Because I've seen a few RISC-V devices where it was just not very good, even though they supported PMP and so on.
Yeah, I'm also a little bit. We're also we know that this in the paper that even though the device key is now hard-coded, it shouldn't be, it should be provided, but yeah, we work with what we have now, I guess.
And did the C920 verify the boot image? Because I've seen with other ones, they tried to implement secure boot and then just didn't verify the boot image. So these things exist on RISC-V.
Yeah, so the thing is, the tests were not flushed on it was done with the NASD card, but yeah, we didn't have any problem by verifying it.
Okay,
yeah.
Thanks.
Questions from the left-hand side? So while I'm walking there, I have a question. You said that your defense prevents software-based attacks. What attacks does it not prevent?
It detects it detects static aliasing, like butt RAM.
Okay. And what
But if you have buttering RAM, for example, which is dynamically, well, this can happen while your machine runs, so not during boot. So if you pass the boot time stage, the mitigation is, yeah.
Okay, so if there are no additional questions, let's thank Antonis again.